I want to talk about the second lab because we have about an hour left in class, and I want to make sure you guys have at least a little bit of idea of what I'm looking for in the second lab. So, and part of the homework is also to deal with acceleration. So the general idea is that in the world, you have the concept of both acceleration and velocity. Gravity is always pulling us down, right? However, you know that gravity makes you fall faster and faster the longer you're being affected by it in the air, right? Like until you reach terminal velocity. So when you jump off a small cliff, you don't fall that fast. However, the taller the cliff, obviously by the time you hit the ground of like a 100-story skyscraper, you're moving really fast, right? Like you're moving much faster than you were at the top, okay? That should make sense. So gravity is a concept that I want to introduce as something in our games that we implement. So if you guys have done the lab so far, up to the point at which we're talking about velocity, we have a ball. We have a ball here. It's in the top left. And it just moves at the same rate. It moves either 100 pixels per second or 250 pixels per second. It moves at a constant rate here. It doesn't speed up or slow down at all. Okay? So what I want to do, though, is that I want this ball to gradually speed up, okay? I want this thing not to instantaneously go as fast as it can, but instead, I want this thing to fall faster and faster, just like it was being affected by gravity, right? So, what that looks like is, see how it like reaches a peak? So watch after it bounces the first time. It'll like reach a peak and then fall and bounce, right? So if I were to show you guys how that looks, right? Yeah. I want this guy to be red. Bear with me while I do this. This is my time. This is my timeline of where my ball is. Oops. This is where, sorry, this is going to be representing, I will do this. It's going to represent the distance line for like where the ball is, and what I'm going to do is break it down so that this right here, t equals 0, and then I have another one here. T equals 1, 2, 3, 4. I have 2 of these. So in my world where I don't have any acceleration, the ball is going to be moving in my graph in one direction from left to right. And it's going to be moving at a constant rate of 1 unit per second. Each one of these t represents 1 second of time. Okay? So at t0 is here. At t1, it's here. At t2, it's here. T3, it's here. T4, it's here. My velocity here remains constant, right? It says move right 1 unit per second. What if I wanted this thing to gradually move faster and faster over time, right? I still am moving to the right, but I'm also going to be moving faster and faster the longer it goes. So if I say I want to apply an acceleration that every time after 1 second, I'm going to move a little bit faster. So here, my velocity is equal to 1 per second. My acceleration here is equal to 0 per second. That's this top graph here. If I want to say instead have a velocity of 0, an acceleration of 1 per second to start. So what does that look like in this graph here? Time 0 is not moving at all. After 1 second has passed, my velocity gets increased by 1. Okay? So right now my velocity is 0. I'm going to let 1 second pass. My acceleration gets put into my velocity. So now my velocity goes up a little bit. It goes up to 1 per second because I've added acceleration into the velocity. So now my ball is moving at a rate of 1. Cool. Next time, I'm going to add acceleration into velocity again. Okay? Acceleration affects the velocity. So what I'm going to do is I'm going to take this concept here, I'm going to add 1 more to my velocity here, 2. So now I'm going to move my ball to here. I'll do it 1 more time, right? I'm going to add acceleration into my velocity again. Now my velocity is 3. Okay. So now I need to move this to make room. My velocity is 3 per second, so it goes 1, 2, 3. Can you guys all see like how at the top here my sphere is moving at a constant rate, right? 1 per second. Down here, what actually happens is that even though my graph here is correct, these times are not. This is time 2. Move this. This is time 6. This is time 2. So if we compare the times now, we're on the bottom here. This is at 1 second. They both match. They're both in the same position. After 2 seconds, the ball that was moving at a constant rate is here. But the ball that had acceleration has moved further than where the ball without acceleration has. Same thing for 3 seconds. After 3 seconds, that ball has moved much faster. Right? The ball is currently moving that much faster. So the general idea is that the way that acceleration and distance work is that distance is a factor of velocity times how fast, the velocity which represents how fast you're moving, and how long you've been moving for. Okay, that's how much distance you've traveled. Right? If I'm moving 50 miles an hour and I say that I've been moving for 1 hour, how many miles have I gone? I have 50 miles an hour, okay, miles per hour, and I've been moving for 1 hour. What's my distance that I traveled? 50, right? So velocity here is also a factor of acceleration. There's actually a formula here for acceleration. It goes 1/2 at squared. This is something that you will learn in physics. I recommend that you guys understand how these two things relate to one another. But if you want to know how fast you're moving, given that you've been accelerating for an hour, let's say I have a car and I'm flooring the car. My car accelerates at 30 miles per hour every hour. If I was holding down the accelerator for an entire hour and I had unlimited horsepower, right? Imagine that my car was like a Bugatti or something like that, and I was flooring the accelerator for a really long time. At the end of like 10 minutes, I'm going much faster at the end of that 10 minutes than I was at the first minute that I was moving. So my velocity is increasing at an exponential rate compared to my distance here. So when you're dealing with this in code, it's actually a very simple concept here because you don't actually need to do any kind of complex math to figure out how fast you want to be moving. If I'm in my code and I say that every frame I'm moving my sphere a little bit, so I have my sphere. And it's moving 100 pixels per second to the right, it'll always just be moving 100 pixels per second. This is my velocity. How do I add this into my position? Well, in code, let me do this in code here. This is basically what you guys have been doing in lab so far. Get rid of all this. 100 pixels to the right. This is my shape moving to the right 100 pixels per second. Right? That's moving at a constant rate. This represents my velocity. So I can have a variable called velocity, which is equal to 100 here. Use that here instead. What happens if I increase the velocity every time I go through this loop? I'll just add 1 to it. Watch what happens to the sphere here. This is me not changing the velocity. This is me speeding up the velocity. Watch, I'll just do this. I'll set the velocity equal to 0, so it's not moving at all. Watch what happens to how fast it's moving. Right? It starts at a standstill. Let me slow it down a little bit. Imagine that's like a car that's like accelerating up. I can also reference this. I just add a number to this. The faster this number is, the faster this variable changes, and the more I move every frame. So this little number right here represents my change in the velocity every frame. What I want to do is I want to change the velocity based on delta time. So what this says is I'm going to increase my velocity by 100 every second. So every second that passes, it starts moving 100 units per second faster. If I print this out to the screen, look at the console on the left here. That's how fast the ball is moving, pixels per second. Okay? The speed at which it's moving gets faster and faster. How does this affect the position of the ball? Look at the actual ball as it's moving. It starts off slow and then goes up and up faster. So what if I printed out the position of the ball? Do this down here. So I'm printing out both the velocity, the speed of the ball, and also where the ball is into. Okay. I'll do this a little bit slower. Now what I'm going to do is I'm actually going to chart this. I'm going to show you guys here. And I'm only going to do 100 of these moves. Or maybe 500 of these moves. I want to show you guys the relationship between position, velocity, and acceleration here. Okay. So I did 500 of these moves here. So it's a little hard to tell here in the numbers, but I'm going to show you next in a spreadsheet and a graph, like how these numbers change. What you'll actually see is that the position here starts off moving slowly. See how it starts at 38, goes to 39, 40, 41, and eventually it starts moving 1 per frame until it eventually starts moving down here. Every frame it moves a lot more than what it did. So here you see I actually jumped like half a unit here, as in the beginning here it spent several frames moving. So let's draw this out in a spreadsheet, which is my favorite thing ever. I have my 3 columns here: position, velocity, and acceleration. Okay. Position here is going to represent a number. My velocity here is also going to represent a number, and my acceleration is all going to represent a constant value, 10. So what I'm going to do here is this is going to be equal to B2 plus C2. Will I get this? There we go. Like so. So here's my velocity. If you see here on the left here, this represents time. My velocity is increasing, right? It's going up every frame. My position oops. So look at my position here. It starts at 10. It moves 10 units per second. Then my velocity goes up to 20. So we add 20 onto our position. So it goes to 30. Our velocity gets increased again. So we add 30 to our position. Then 40 to our position. Then 50. Then 60. Then 70. Then 80. Then 90. We start adding a lot bigger numbers over and over again. What happens to our acceleration here? It's constant. It doesn't change at all, right? This is gravity. Gravity is always accelerating us downward at a constant rate. Let's see if I can do this. If I blow this up here, let me get rid of a few of these because it's too much. So here's my chart here, which represents the 3 pieces of movement for my ball in the game. The blue line here represents the position. You can imagine that if you flip this chart upside down, or the ball was moving upward, like accelerating upwards, that the ball is moving in a curved format. It's moving exponentially faster. There's a curve associated with it, not straight. The velocity here is actually moving linearly faster. So like every frame, it's moving at a steady rate without increasing more than 10 per second. Whereas acceleration here goes at a very constant 10. It never changes. Okay. So the way this applies to code is that I have my velocity here. This is just like my spreadsheet. I'm going to add 50 into my velocity every frame. And then I'm going to take my velocity, and that's what I'm going to use to move my shape every frame as well. So the bigger this number is, the faster it accelerates to go to the right edge of the screen. So I can make this number quite large. And it always will start off at 0. However, the larger I make it, the faster it spins off outside the edge of the screen. Or I can make the acceleration really, really small, and it will take a while, but gradually this thing is moving faster and faster every second. This is like Bowser in Mario Kart. It takes a while for him to get up to speed. So what I want you guys to do in lab is I want you to apply this to your ball. So gravity is a concept I want you guys to think about as a pixels per second concept. I want a ball in our game to move with gravity involved. So I give you guys some instructions on how to accommodate for velocity, but that thing needs to look like a ball falling with gravity. So here I give you guys like 500 pixels per second or 1,000 pixels per second. And I want this thing to accelerate downward. So it's going to start at rest and then fall as if it was a ball that was dropped. Okay. So in order to do this lab properly, which I want you guys to do, is you guys also need to do the last part of lab number 1, which is bouncing off the walls. Okay. This is related to the previous part of lab where every time you press enter, it like changes the direction of the ball. You're going to use the same exact idea, except instead you're going to make it bounce off the edges of the screen. Okay. All right. I know there's a lot there. However, what I want you guys to do is